In the previous episode, we finished off by talking about 8086 and 8088, if memory serves me correctly. They were
Yes.
basically the beginning of the x86 instruction set. And basically what happened as those two came to the market at the same time, there were a couple of really important market movements. We're going to talk about IBM PC and the clones and Clone Wars in some of the later episodes, but that's less relevant for our discussion right now. But these two were like first x86 CPUs. They had the first revision of the instruction set architecture that we nowadays still call x86. And basically all of the CPUs after that had them as well. But those CPUs are relevant for as history, let's say, bullet points. What's coming next is much more important because the next four generations after that, and then the next generations after that, and more than a few others afterwards are even more and more important. But looking into the topic that we are going to cover today, I read some materials. I found a very good book for it. I'm going to reference it in the description box. I actually realized that the vast majority of the CPUs that we are going to be discussing today are actually 80s designs from the 1980s, which is really cool, as I usually consider 80s to be the best era for more than a few things, not only for the advancement in the CPU design. But okay, let's have the discussion a little bit later. Welcome to the new episode of That IT Show podcast. Let's roll the intro, and then we're going to start talking about the 80, 186, 286, 386, and 486 CPUs. Okay, before we start, just like last time, I have a couple of questions for you, Mr. Computer Architecture.
Okay.
Yeah, we have to start with
Okay.
something. Let's start with the first question, which is going to become pertinent in our discussion later. So the first question is, what does it mean that CPU has L1 cache, L2 cache, and what the heck does that have to do with CPU speed?
I have absolutely no idea.
Yes, you do.
Because when it comes to CPUs, the water is so murky when it comes to caches and what it means to have L1, L2, L3, and so on cache, that it's hard to tell. But let's try to be simple and say that all the things that the processor needs are stored in the memory. Whatever you're doing and whatever architecture you're running on, you would like for memory to be quicker because the memory is usually a couple of orders of magnitude, if even slower than that. And then you are always waiting for the memory to come up with the data that you're waiting for, so the processor is basically waiting. And one of the solutions that can be done to mitigate that problem, not solve it but mitigate it, is creating caches. And caches can be multi-tiered, so L1, L2, L3, and then all the derivatives thereof, because once the processors became multi-core, suddenly we are stuck with the structure of the cache memory that is much more complicated than that what probably almost all the people understand, including me.
Okay. Next question also is going to be quite pertinent for our discussion. When from generation to generation, Intel introduced new instructions. Basically, every single new generation, 186, then 2, then 3, then 4, brought some new instructions. What does that have to do with anything? What are the instructions and why are they important?
So let's go back, since I'm doing the computer architecture course today. Let's go back to the main things that we were talking about last time. Instructions, or each instruction, means circuitry. Once you need to put circuitry on the silicon, you suddenly need A, power, and B, space. When you are introducing new instructions, you are creating more complex circuitry, and this means that you are going to be wasting more and more power doing something. So what the nice people who are designing processors did is that they decided to go two different ways. One is to try to solve the problem with instructions by putting everything in silicon. So basically the Intel way of having multiple thousands of instructions that do almost everything in the processor itself. For example, there is an actual instruction that is able to search for a character in a string in the memory directly from the processor. The other way that some of the designers decided to go was to create as small of a set of instructions as possible, and then to implement everything, if possible, in software, even including some of the things that you would probably expect in the CPU. For example, ARM didn't have a divide instruction up until the version 7, I think. The divide was implemented as an instruction that was basically a software library that you could include, and it was assembled by utilizing the instructions that they had. So the thing is that if you are pushing for more instructions, you are creating an environment that is easier to program, or is supposed to be easier to program, but at the same time you are creating a problem for yourself because you are creating enormous chips.
Okay. Well.
Sorry.
Yeah, it happens. It's okay. You've been talking a lot in the past couple of weeks as well, and you were sick as well. And
yes.
Further than the last question for this episode, what kind of a difference does the FPU unit or floating point unit make to CPU performance? Because this is going to be a reoccurring theme in this episode, for obvious
reasons. But to be completely honest, it doesn't do anything for the CPU performance.
Okay.
It does for the app performance, because once you start running apps that for some reason need mathematical operations, and by that I mean graphics, that I mean 3D modeling and so on, suddenly you are beginning to deal with a lot of floating point numbers, so numbers with decimal places.
And for that reason,
and floating point numbers are something that is complicated to do in this chip. So you need a separate unit. Anyways, so suddenly when you are dealing with the FPU or the floating point unit, you are dealing with a specific part of the chip that is able to do arithmetics outside of the normal binary notation arithmetic. And it needs to do it using the specific notation that is able to write down the numbers as floating points. So basically, what you're dealing with is you're trying to create a CPU that is able to deal with decimal numbers. By decimal, I mean numbers that have remainder and have fractions. And fractional numbers as such are complicated to deal with because you are dealing with translated into binary, so you are inevitably going to lose some precision. And this means that you are going to be stuck with trying to calculate something that is necessarily going to introduce errors into calculations. If you want to mitigate those errors, you can deal with floating point numbers that are bigger, so you allocate much more memory to store the floating point numbers. But then you have another problem because you are suddenly dealing with 64-bit or 128-bit numbers that are much more complex to deal with. So what people did, and this was a specific thing that I'm going to point out because this is one of the things with 8486, is that they introduced a specific part in the CPU that was dedicated to just do the floating point arithmetic and nothing else. And a lot of, at the time, so it was end of the 80s, a lot of the different manufacturers did it the same way back way then. They either did it inside their processor, or they created a coprocessor that was able to do the floating point. And this was the reason why in the end of the 80s, coprocessors as such were a thing. Today, nobody remembers what the coprocessor is.
Yeah.
But back way then, 84860 was something that you could actually buy. and coupling that with a regular SX version of the 486 meant that you could get a separate multi-point instruction unit. Of course, you could also get an integrated unit into the DX chip. So Intel offered two things.
Okay.
Now,
yeah.
Since I answered, I did the how did I do, Professor?
Pretty darn well. I'm very happy with your answers. You have the potential to get a B.
Okay, so now let's completely skip over some of the parts, because, as you know, I usually start from the middle. And
let's start at the beginning.
Let's talk about one thing. I want to put into perspective the years, since you said that the design of the chips was something that came from the 80s. Let me just quickly do some mental arithmetic that is completely outside of what is normally done when we're comparing processors. So 386 came out in 1985. The next generation came out in 1989, 486. The Pentium was 1993. There was a saying, or a design policy, that Intel was keeping up way back then, in the way that they always said that once they are introducing a chipset to the market and chips to the market, they always have the next generation ready. Not production ready, so technology is there, but the producing of the chip, the production in numbers, is usually not solved. But they have the next generation ready for the market.
Okay.
And also they have one since the team that has introduced the new chip is now free. That team is also already doing the next generation after that. So basically, when they're introducing a chip, they have a chip that is ready, that is not being introduced, and the next generation after this.
Okay.
So if you take into account that the 486 was introduced in 1989, this means that the Pentium was ready, and Pentium Pro was also designed and ready. So it's not unusual, or I would expect that all the design that came out in the up to the middle of the 90s was basically the 80s design.
That's a very good point.
Because I wouldn't be too surprised if I learned that Pentium Pro was probably the first one that was designed mostly in the 90s.
Yeah, that makes sense. Yeah. They never you cannot design a CPU in a month. Those days were long gone by then.
Okay, now a quick question for you. Which of the old CPUs that we are talking about is still merely running on every motherboard available right now?
486.
Yes, where?
Some things related to the motherboard, some of the remote management softwares and whatnot, if I remember correctly.
So in Intel's management engine.
Yeah.
IME.
Yeah, that's good.
And this is something. This is one of those technologies that nobody knows about, that can be useful, but nobody knows how to run it,
or what to do with it until, as I found out lately, until you start playing around with some of the more advanced features of it, with the vPro and all of the things that came afterwards. When you start pixie booting and whatnot, and all of a sudden you discover that there are some really cool things there. But perhaps a topic for another episode. That's a very, very cool thing to discuss as well, because both of us have loads of experience of remote starting a lot of unnecessary things and necessary things as well. Okay, so
I'm going to go so off topic completely and just say one thing. Nowadays, I'm dividing everything that I'm working with into can be managed remotely and cannot be managed remotely category, and I'm trying not to deal with the later. So,
of course,
if I cannot manage it remotely, or to be more precise, if I have to travel somewhere to kick part of the hardware, this means that I'm disinclined to try to run it.
No, you just want to deal with the remote stuff, and stuff that's not remotely accessible, somebody else needs to deal with that.
So I need remote hands.
Yes, you need remote programmable hands. I have a
yes. Anyways,
I want to ask.
Go back.
Yeah, I want to ask you a question. So related to 186 and 188. So this is the only product that I never saw in the wild, actually, in a computer, which is not all that surprising because it was meant to be some kind of a, let's say, CPU for, let's say, embedded or stuff. But there were a couple of computers that were made by a variety of manufacturers like Siemens and IBM and Tandy and HP and Philips, whatever. So this CPU was introduced in 1982. The question for you, do you know when Intel retired the production of 186? Because it's going to blow your mind if you don't.
But since we already were talking about that the production of the 8086 and 8088 was done in 2000s, so I wouldn't be surprised that we are talking about probably 10 years ago or something.
2007, basically 25 years. And they made a heck of a lot of revisions to that, and there were advanced versions with, let's say, faster clocks and whatnot. So I found out about this today when I was reading a book, and I was just completely astonished because, again, going back to my point from 2 minutes ago, I never saw a computer that had 8186 anywhere.
But this was because the when I was trying to search for what was running the 8186, basically it wasn't even mentioned when it came to anything remotely connected to home PCs.
Yeah.
It was embedded systems, printers, industrial systems, communications, switches, cars, military, and so on. But none of it mentioned any desktops.
Yeah.
So the design itself was, I think that the reason was that design was created as an enhanced version of the 8086. And I think that the reason why it got hold of all the embedded systems is because of the way that they are designed. When people are designing embedded things, they usually tend to stick to all technology that works. And they are much more inclined to just wait, 4 or 5 years to see what is going to work, because usually their goal is not the speed, their goal is stability. So they got an enhanced version of the processor that was good. So they basically decided that they're going to just be sticking with it and continue to do it. Because if you don't require speed, I would guess that 2007, the version from 2007 of the 8186 would be extremely small, extremely fast, extremely stable processor that would probably not only not require additional cooling, but would be probably capable of cooling itself and the surrounding area of the
yeah, somehow pulling heat into itself as how cold it is. Yeah, actually, I found a paper somewhere on the net stating that the latest revisions of that CPU, dating to 2006, 2007, latest designs of them before retiring, were running at something like 25 megahertz, which, if you put into context, because the original ones were, I don't know, 6 or 8 megahertz, whatever, that was enormously faster than what the original designs were.
Yes, but I think that the reason why you are not seeing it is because the people who wanted it were people who were requiring stability. And 286, although not that important, if you ask me, was the processor that introduced the protected mode.
Yeah, there was actually one other big reason why 186 was basically an abysmal failure when looking into PC-based designs. There's actually a timeline thing that happened right before the 186 was introduced, because IBM launched the PC in August in 81. Okay,
yes.
And they selected 8086 and 8088 for that. So basically, if Intel wanted to have 186 or 88 as a part of that platform, they were 6 months late. And the problem was the fact that IBM managed to sell during those 6 months from August to February or whatever it was when they launched 186, IBM managed to sell, according to the data that they found, something like 60,000 PCs, which back way then was enormous amount.
But also the thing was that 8286 came out the same year as 186. So it was obvious that they are going to be dealing with that. They were dealing with different processor. I would guess that they had a team that was dedicated to creating 8086 enhanced, and the other team that was dealing with the 8286 and trying to put new features in it, because the clock was much quicker. The protected mode was a thing that we kept using for the next 20 years or
24
so.
years, yeah.
Unfortunately, we still have to use it.
Yeah.
Because this is one of the ways to boot the processor into 64-bit mode. Still, Intel is trying to get this thing out of the ISA by creating the new proposals of how to boot directly into 64-bit mode, because they're trying to solve the things that were established when the 286 was designed. But having said that, let's talk about 286 first.
Yeah. No problem. So this is something that if I found materials on Intel's website stating that they started development of this in 1978. So 4 years prior to launching 186 and basically 286 as well. They considered it to be something like, let's say, a next generation of 8086 yet again. A lot of people were writing at the time. I remember some of the early bytes that I read way when I was I was much younger, but still later after that was all introduced to the market. They consider that CPU to be aimed at the multi-user multitasking environments, 286. I mean, looking at the tech spec from the eyes of the 80s, having in mind that it could do it was a gigabyte of memory in the second mode and 16 megabytes of physical memory, or whatever, 1 megabyte of physical memory and 60 of virtual, something like that, if I remember correctly. This was actually the CPU that kind of merged the idea of what Intel wanted as a CPU and IBM's visions of the PC. That's where the PC AT was born, if you remember those days.
Yes, but the thing is also that protected mode did one thing, and this is that it actually enabled you to do multitasking.
Yes.
So you were able to deal with the memory and solve the problem that all the previous CPUs had. You could call all the previous CPUs stupid, basically. And by stupid, I don't mean that they had a problem. I mean that they weren't able of doing anything other than a single task in a single CPU cycle. So basically, you couldn't. There wasn't a way for the CPU itself to slice the time or slice the cycles into manageable pieces, because there was no way to identify those pieces. And once the protected mode came to be, you were able to actually assign and manage tasks in memory. So this created a way for people to actually make operating systems that made sense. Up until then, CPM was the same as DOS, and they didn't provide you with the capability of multitasking at all.
Okay, unless we're talking about TSM programs, but that's again a topic for a completely different day. I would ask you a question here and right now, because you mentioned the real mode and protected mode and whatnot. Having that in mind, so I'm setting you up for a good explanation now. What was the biggest problem of 286 looking at those modes? If you remember.
The need to switch.
Okay.
I think that the biggest problem was that you could switch one way, but you couldn't switch the other.
What did you need to do to go back to real mode?
You had to reset the processor in its entirety.
Yeah.
And it was a big problem, because you actually had to more or less start from the start, so boot the entire processor in order to switch back to protected mode.
This was a major pain, basically, for everybody involved. And the second thing, and you kind of hinted at that. Basically, when you look at the way in which the real and protected mode worked, specifically looking at the protected mode, don't you consider that to be basically the introduction to x86 virtualization?
Yes and no. I think that the thing was that suddenly what happened is that people realized that the design is going to split into two ways. One is going to be designing the pure silicon, so you're going to be designing the CPU itself, but there is going to be another team that is going to be designing the infrastructure and the idea that the ISA is going to follow. Because suddenly people who were designing processors decided that they're going to create processors that are connected directly to the workflow of the programmers. So they were actually trying to solve the users' problems. I think that you could say, and this is my own opinion, is that before I would say 81, 86, so before 1982, the designers of the processors haven't had any idea what they were trying to do. They were just solving the problems and creating a thing that works. And then they got enough horsepower under the hood that they could finally start to plan. They could design chips that were designed for something, and they could introduce instructions that made sense for the programmers back way then. They could talk to the programmers to create infrastructure that would support new operating systems, that would support new ways of programming. Because as always, the problem with programs is that they are compiled for the architecture that you have. And once the architecture changes, you either recompile the program, or you have a program that is compiled for the older architecture.
Tangent question. Do you know which was the first CPU in the Intel stack that was actually touted as something that needs recompiling for, and recompiling resulting in usually like, let's say 20, 30, 40% faster code? Do you remember?
I will guess Pentium Pro.
You are almost correct. Pentium. And then Pentium Pro. Pentium was the first.
I would guess Pentium Pro, because Pentium Pro was the one that had a lot of cache, and it was the one that created out of order execution.
Yeah, and superscalar Pentiums were first superscalars as well.
Yes, and the thing was that if you wanted to enable out of order execution, there is no other way to do it other than to have the compiler that is capable of doing out of order execution, because actually there is no other way to convince the CPU to do it by itself.
Yeah, okay. So that a couple of questions that I had about that successfully answered. You're still at the B, maybe progressing towards A minus. So not a bad job.
Okay.
Basically, we were talking about real and protected mode. So by adding the protected mode, what Intel basically did, they were getting ready for the future. I mean, the world was back then utterly dominated by those applications. Windows were not a thing yet. They were on the horizon, coming up. And in the next CPU generation, which was 386, they added an additional mode. So it wasn't only a real mode and a protected mode, they added another one. Do you remember that one?
Yes, I remember the mode, but I don't remember the name.
It was called virtual mode. They call it virtual real mode or something like that. So virtual mode was added. Basically, by adding these capabilities, protected and virtual mode, what they enabled us to do, in simplest, Joe from the street terms, was when Windows came out, we could just start, let's say, a host of DOS applications in DOS Windows and run them, because it kind of sliced the environment into multiple parts, with multiple different registers being used, per, let's say, CMD that you started, or Common COM way back then, and it was actually usable. Although, if you want to look at the history of operating systems, as we covered in one of the previous episodes related to OS2, OS2 was the first one who did that efficiently.
Yes, but also there is a question for you. Mm-hmm. Do you remember the decision that they made when it comes to memory that came later to bother them a lot? Do you remember when they were trying to deal with more memory, or increasing the available memory space? what they did.
You mean 640 plus the rest or something else?
Yes.
Yeah, I remember those days very well, and not in a
Yes,
good
you
way.
remember those days, but do you remember how it was done?
Yeah, by loading some of the additional drivers in DOS, like high memsys and load high, load mem high.
Yes.
Yeah, I remember all of those things.
And the thing was that it was done by segmenting the memory.
Correct.
And nobody does that anymore. Everybody did, and everybody does paging, because paging is much easier to do and much easier to keep track of.
Yeah.
And the reason why it was so complicated to deal with memory back way then was that the processors themselves weren't capable of the paging. They had to do segmented memory, so you had to segment the memory and then talk to it. And this was a big problem, and it was less efficient than any other way of dealing with the memory.
But the 286 had a memory management unit. This was the first CPU, if I remember correctly, that had a memory management unit. But of course, new technology, it did require quite a bit of time for that to be efficiently used. So that much.
Okay, so now that we have, I think that we have finished 286.
You think?
Let's introduce introduce 386, because this was the one that was the first 32-bit.
Yeah, 32-bit CPU. Yeah.
Yes,
I was about to harass you with more 286 info, but okay.
No. Go on. If you have anything important to add.
I have a couple of just semi stupid jokes and a couple of notes that I kind of remembered when I was scratching through the banks of memory that I have in my head. Actually, one of those memories is related to protected mode. As you said, this is the basis for all of the multitasking that we do, which doesn't have the 1 megabyte limit as we used to have in the real mode. So as a result of that, again, as you mentioned, we have multitasking capabilities, virtual memory support, better I/O, all of the things that you mentioned. But
yes,
at the time when 286 came out, it was completely unused and misunderstood concept by most of the early versions of Windows. And as a result of that, we got a lot of good old memory protection fault errors, if you remember. Those days, I remember them vividly.
Yes, this was one of the things. And the other thing was that the compilers couldn't keep up.
Mm-hmm.
The reason is that you must put things into perspective. From our perspective today, compilers can be updated basically every week. If something new comes up, Microsoft is even capable of actually releasing a completely new version of the operating system, C under Windows 11. And nowadays, it's not uncommon that you can actually get a compiler for the new architecture even before the architecture is launched. Back way then, the architecture was launched, then you got the compilers, and then those who were able to update the compilers compiled for the new architecture. The rest of them just simply compiled for the old architecture and hoped that it is going to work. And this is where back compatibility was stabbing Intel in the back, because you were able to do the compiling, but you weren't using almost none of the features that the new processor had.
Yeah. Okay. Go ahead.
Okay.
You wanted to add something?
Yes, I also want to add one thing that was extremely annoying to me, was that with 286 came I think this was the golden era of the turbo button.
No, it was, for me it was 486, but yeah, go ahead.
Yes, but it was the golden era of turbo button because 286 was much quicker than the old XT as it was called, so basically 8088. And what you got was a much quicker processor, and combining that with the miscompiled or programs or applications compiled for the older version of the processor, the actual turbo button made some sense. There was some sense in trying to downclock the processor in order to get some of the applications
to make Tetris work.
To make Tetris work, to make all the old games work, but also to make some of the applications more stable.
Yeah, you are exactly correct. I just remember one more thing. If I remember correctly, the 286 was basically the last Intel CPU from the era in which Intel was willing to license things. After that came all of the lawsuits and all of the hoopla related to that. So that's the first thing. And with 386, we already had lawsuits, and there were quite a few of them. But more to your point, excellent point that you made, which is OS design and compiler design didn't necessarily keep up with the stuff that was happening on the hardware market afterwards. There are things happening right now on the market that are basically going to also bite us heavily yet again, because of the misdesign of the concepts in the operating system. As you had the chance to work with some of the AMD epics in the past couple of years, you know that they have a lot of CPU cores and even more threads. And modern OSs, it doesn't really matter which ones. Are you talking Windows Server, Windows Client, Linux, whatever? They are suffering from some of these bad habits, let's say bad code, and the things that are limiting them from using the resources of, for example, 128, 256 core CPUs and whatnot. And this is a topic that we will cover in the future because it's very, very present right now.
This is also the reason why I'm keeping and I'm keeping I'm keeping my calm being on Windows 11, because I think that Windows 11 is an actually interesting operating system if you are using the latest two generations of Intel.
Thread director and all of the other beautiful things.
Yes. So when you have asymmetrical cores and you have new generations of Intel or new generations of AMD for that matter, you are going to get something out of using a new operating system. And that's not something that you can get out of using anything other than the latest one, because the multitasking and the way it is being dealt with the inside the operating system is different when it comes to new processors.
Yes.
So I will say that I'm not happy with Windows 11 itself, but I'm happy with actually running a technology that was designed for the chip that I have.
Okay, I agree. Okay, here comes your baby, 386. You want to start or should I?
I already started. The 386 was the one of the most influential chips because it started the 32-bit. It started mainstream 32-bit implementation, because a lot of other chips already had 32-bit capabilities, but this was the first one that was designed for the desktop.
Mm-hmm.
So personal computing and actual desktops, people's desktops.
Mm-hmm.
So multitasking was introduced. Memory address space was much larger, and it started something that made sense at the time. That is, it started Intel's let's say regular updates of the CPUs.
Okay, it started something else, which I think both you and I are going to agree is very, very, very annoying. We had the S6, we had the DX, then DX2, then DX4, which was actually a DX3. We had 386EX. We had sub-variants of all of those. We had 16, 20, 25, 33 megahertz models for most of them. Then we had AMD AM386, which went up to 40 megahertz and whatnot. There was like a litany of models, and nobody knew what to choose from. And I'm especially looking at the S6 variants of that CPU, because they were pissing me off as a young dude so much, because of the lack of the FPU, as I'm sure you know. But it was making our choices difficult. A reoccurring theme all the way to this day.
Okay, yes, but it was there were reasons for that.
I know.
You know that the main reason was manufacturing.
Yeah.
Because the manufacturing of the 386 was expensive, and they had to bin the processors in any which way possible to enable them to sell them. Mm-hmm. So there were even those processors that would probably not end up on the market because they were not unstable on the given speed, were just thrown in the market with a much more slower speed, just to get them out and to make production possible because they weren't losing money, but they were close to it. So they were trying to lower the price of the CPU, and this was the reason why they did it. Also, they had a big problem because the advanced features of the 386 were something that people weren't used to. I would call it that. Okay, so 386 didn't have a floating point processor. 486 was the first one that did. The thing was that since the processors themselves didn't have the floating point units, almost none of the programmers did floating point because it didn't make sense to do it. You had to do it either completely in software, which was slow, or you were trying to avoid it at all costs and try to make deal with whatever you had available. Because running into floating point meant that you are going to be running into much slower applications, and your functions are going to be performed much slower. So let's talk about other things in 386. They finally introduced paging.
Yes.
Which was the thing that they were able to actually switch in and out pages of memory, which meant that they were able to switch applications. Which meant that they were able to easily and simultaneously run multiple applications on the same chip.
Multitasking.
Yes, the mode that you mentioned virtual mode. So the mode that was actually okay. They enabled you to switch between different modes without resetting, which is a major step forward.
Yes.
Although it didn't make sense at the time, but it was a major step forward. But the thing was that I think that the biggest thing was that the people had a lot of problems accepting the new technology. And one of the reasons was, if you remember, that this was one of the first chips that required cooling. And this was something that people weren't expecting. Before that, if you remember the computers before that, they actually were just
passively
chips.
cooled.
You just had a bunch of chips on the motherboard, and that was it. The chips could be completely distinguishable between one and the other. Had complex new technologies, complex new modes, complex ways of talking to the memory, and so on. So it was a problem because you needed new compilers. You needed new operating systems, and what was the worst thing? You needed new programmers.
Yeah.
You needed people who were able to understand new technology, and since this technology was done in a different way, and now I'm going to just be okay. Now I'm just going to be mad at people who don't understand that programming sometimes requires you to think, not go and Google for a new framework. So we had one of those. We had one of those a couple of days ago, where a student of ours was asking us why he's unable to do something in 2D because there is no support for 2D in 602 processor.
Oh yeah, I remember.
So when you don't have the finished libraries, when you don't have pre-prepared compilers, you actually need to learn how the processor works, and this took time. So 386 was slow to the market when it came to new applications and the support in new applications. Almost all the applications on the market first started with just being run on the faster processor and just being faster simply on okay, the new processor is faster, so the application runs faster. And then came the actual benefit of running on new modes, using more memory, and so on and so on. And this is not the first time that we have seen this.
Yeah, nor the last.
Yes.
Yeah, and yeah, this having said that, this was a switch to 32-bit technology. That meant that we could address 4 gigabytes of memory, something that we are going to have like a reoccurring theme all the way till we start seeing 64-bit CPUs and operating systems and various solutions, which we will cover in the later episodes. But back way then, as I mentioned with the 286, we actually had a couple of different numbers that were very interesting to us. It could address X amount of memory, and it could also address X amount of virtual memory. Those were the numbers that were very interesting to us, along with the MIPS and the amount of transistors and stuff like that, which we used to kind of like have a gauge on how performant the CPUs will be. And this one was, at least on paper, was capable of doing 64 terabytes of virtual memory, which was a huge jump when compared to the previous generations of the CPUs. And in terms of speed, it was basically double, like 2x the speed, or even more, depending on the application, if programming was done correctly.
And the thing was with the virtual memory and the virtual modes and virtual everything, is that this was the first time when the programmers suddenly realized that they are going to be separated from the hardware itself, because they are going to be writing the applications and they're going to be creating code that is going to run on something that is not going to be there. They're not going to be writing code that is going to be run byte by byte the way they design it on the CPU, because the CPU itself is going to decide on some things, and the CPU itself is going to help them run some things. So this is one of those things. It made sense when it came to that part of the I would say cycle of new processors, to slowly start peeling the programmers of the CPU core and make them do things that are I'm searching for the word. I would say more abstract.
Mm-hmm.
They were trying to. They were there to create abstract concepts, not to run, not to play bit by bit games on the CPUs.
Mm-hmm. Okay. Any other things you want to say about 386, or should we move to 486?
No, because I want to mention the 486 for all the things that it was
super important.
It was super important.
Okay.
And I think that the first thing that I want to mention is that it was the first one that faced immense competition.
Mm-hmm.
Because 386 had competition, but the competition itself was not that bad, not that good. There was Cyrix, that was who was also
IBM
on the market back then.
AMD,
AMD, and so on. Yeah. But 286s and 386s, especially the ASICs, parts were much slower and much. They weren't competitive enough when it came to Intel.
Mm-hmm.
486 was first. They had the rest of the gang had competitive processors.
Mm-hmm.
AMD especially,
mm-hmm.
that was much cheaper, if you remember this.
Mm-hmm.
The systems and the 486 models were switching speeds and moving speeds up much faster than all the rest of the processors.
Mm-hmm.
So you could actually gain some speed by just getting a new part that would have, I don't know, I would call it order of magnitude, but double the speed or triple the speed of the previous processor.
Mm-hmm.
And the thing was that it was much more expensive.
Mm-hmm.
Much more expensive, because if you wanted to buy a DX version with the floating point, which more or less didn't make sense,
mm-hmm.
You had to pay much more than for the 386 comparable model.
Yep. Actually, let's try to do this a little bit in reverse. If you were to think about the most important, let's say, 3 or 4 things that you would relate to 486, let's say CPUs, what would your standout features be? Let's have a discussion. I'm going to name mine and agree with you or disagree or add some more. What do you think are the most important features of 486? Let's say.
It's easy. First, the obvious one is not the floating point.
Mm-hmm.
The obvious one is the pipelines.
Yes.
The pipelines, I think, is the most obvious one, and the thing that actually was the turning point when it came to processing. Also introducing cache.
Yeah, I would say cache is the most important.
But I would call it a pipeline because
Okay.
once you have to introduce pipelines, you have to introduce cache. And so the cache itself is just a byproduct of introducing pipelines.
Okay.
But they didn't need to introduce pipelining, and they didn't need to try to mess with the order of execution of new instructions. And this was the first time when they actually did, and when they actually created an environment that made sense and made use of being able to execute the instructions. It wasn't out of order, but in parallel. So they were starting to learn how to speed up the execution in ways that made sense way back then, and these were, from our perspective today, the obvious things to do.
Yeah, the most of these things that we just mentioned in the past minute are still being used today.
Yes, but this is just the first thing.
Yeah.
This is the first thing that you do if you want to speed things up.
Yeah.
If you are unable to do multi-core, if you're unable to synchronize the cores, do out of order, do predictions, and so on, you simply use pipelines.
Yeah.
And this was the time when they did it.
Okay. One other thing which I find to be important from the user's perspective more than perhaps a technological perspective, although I'm in no way diminishing the technological prowess of that feature. You went with turbo buttons. Now I'm mentioning not turbo buttons. I'm mentioning X2, X4, basically X3 CPUs, because they introduced the clock doubling and tripling. Although they called it the X4, but it doesn't really matter. So, you had the button on 286 to kind of like go from 25 to 33, stuff like that. In 46, it was a double or quadruple, at least on the paper. It was triple the speed of the CPU. I remember that vividly because I did have a DX4. I didn't have 286 or 386 or 186. I did have a DX4 IBM's. Way back in 1996, I think it was, and you know how we use those buttons. If you did anything that required any kind of production level speed, you just left it on, and if you were playing Tetris, you were slowing it down if you could. That was it. But even then, it was too fast.
Yes, but it was first of the processors that were slowly losing the concept of we are going to use the processor 100% of the CPU cycles in order to be able to run anything.
Okay.
Because if you think about the processors way back then, and way back then I mean 602 and all the processors up to 1985, 1986. All of them were designed in such a way that when you started the processor up, it was executing instructions at 100% of the CPU availability. That was it.
Yep.
It wasn't able to throttle down. It wasn't able to change anything. It would just go on and execute instruction after instruction, increasing the program counter as it went. If you wanted to stop the processor, you needed to stop the processor. But nobody was paying any attention in the processor. Nothing was paying attention to, cool the processor down, have any management of anything that was happening inside. 486 had an idea of having pipelines, so this meant that they weren't always using 100% of the time the processor itself. But after that came the idea of being able to throttle, being able to deal with different speeds, different applications, and so on. And this was partly because the Intel enabled it, and partly because the operating systems enabled it.
Yeah, because nothing happens without the software support. Now, a question for you: what was the main difference between the DX2 and the DX4? Do you remember? Of course, clock speed is the obvious one, but apart from that, from the purely architectural standpoint,
I would say that my one neuron is communicating something about the memory with the other neuron.
it's cache. It's not memory.
Yeah, but something about memory. I don't remember which one. I just remember that it was something about some memory,
Yeah.
but I actually don't know.
Okay, so DX2 had 8 kilobytes of L1 cache, DX4 had 16, double the amount. And again, this is a trend that we are going to talk about and cover in some of the future episodes coming to later in the Intel series as well, because it is impossible to overstate how important the L1 cache, for example, is for the CPU performance if done right.
On the other hand, I'm just going to mention that there wasn't any level 2 cache
Yeah,
because the level 2 didn't exist at the time.
well,
So L1 was the only cache that you had.
Yep.
And from our perspective today, 8 kilobytes was puny, but
we don't
way back
have way more today, actually.
yes, but way back then, 8 kilobytes was a big chunk of memory.
Yes.
Especially when compared to the speed difference between today's processors and the processors way back then.
Exactly.
If the cache grew at the same rate as the processor speed, we would have something probably like in magnitude of gigabytes inside the processor.
Yeah, and we would have to cool that down by using impossible amount of liquid nitrogen or something.
I was just talking to the students a couple of days ago, I think last week, and they were asking me what are the main problems with the cooling of the processors today. And I said that one of the main reasons that we have a problem is that processors themselves are done in a planar architecture. We are
They're
unable
starting
to do 3D.
overcome that problem, and some.
Yes, but we are unable to do the real 3D.
Yeah.
And now I'm waiting for the first generation of processors that are going to be enabled to do the actual 3D modeling. So create 3D pathways through the processor and incorporate the cooling inside this.
and the 3D processors, 3D cache.
Yes, but that's just sandwiching the processor between the memory cells, and that's it. I'm expecting for everything to just suddenly stop being linear and planar, and just start being fuzzy logic designed mess that is going to look like a potato and is going to be basically a potato-sized gigawatt of power.
Yeah, and in your world in which that happens, you have multiple control units in the CPU, with one of them being like linear logic and one of them being fuzzy logic, one of them having constant clock, one of them have random clock. Whatever might happen, might happen.
And I see optics being implemented somewhere in that mess that is going to separate parts of the processor. But let's not get ahead of us. Let's go on and quickly as we can go and skip over the 486.
No. This is where we're going to stop the episode, because next time we're going to deal with at least 5 generations of Pentiums, and I would like to stop here. But you can kind of like give the hint if you want to.
No. I need to stop with the 486 because I want to say one thing.
Go ahead.
486 was the last processor that you could actually break by removing the cooling.
Okay.
And the reason was that this is the last processor that was unable to thermal throttle. And this was one of those things that were actually surprising for me, because 486 was also the first processor that was able to do power saving. So you had separate versions for the desktops and the laptops. Okay, it didn't make too much sense to create a laptop out of it, because those laptops were luggables, not laptops, but okay, that's for another episode and another discussion. But the thing is that 486 was one of those processors that was the last of the kind. It was the last that was actually, I would say, unmanaged.
Okay.
Pentium is much more aware of itself. It is capable of doing reconfiguration of the chip, and by that I mean getting the speed up or down, doing the speed step, doing the thermal throttling, and so on. 486 was the last generation of the chips that were as I would call them, stupid. They weren't stupid, but they were the processors that were basically running full throttle all the time, and then limiting itself by doing the pipelines, and that's it. After this, processors suddenly realized that they can be self-regulated, and they started to do throttling. They started to do management of the memory. They started to do power saving, and so on and so on and so on.
Okay, I agree. You hit the nail on the head. Although there were quite a few problems with some of the next generations of Intel CPUs that are coming after that, especially with the Pentium. Some of the initial releases were notorious for some of the things, but let's leave that for the next episode. Okay, you happy with what we covered today, or do you want to add something else, or are we basically done?
I just wanted to ask, are you going to do the rest of the bunch, the copycats or the guys who are doing the alternatives to Intel in a separate episode, or do we do it now?
No, I would much prefer to have a couple of episodes about that, because the initial part of the Clone Wars and the later part of the Clone Wars, I think, are vastly different to what it was in terms of when looking through the timeline. So I would guess we could do two episodes about that and have loads of material to talk about, because I wanted to do this just Intel only and mention the clones if we need to, but not go overly into that, although I consider that to be one of the most important stories of, let's say, x86 generation of CPUs of all time. And one of the key reasons why we have certain things the way we do now, even now.
I think that the ability of the people or the companies to copy one from the other and to innovate at the time when innovation was actually possible was the thing that actually drew the IT technology forward.
Agreed.
Today, innovating is not that simple. First, you have the IPs. You saw, and I'm going to put the, I'm going to ask you to put the graph somewhere on the screen. The graph that I posted a couple of days ago about the difference between the companies in the last 20 years on the amount of property that they own. So basically, the amount of actual assets that are physical assets and the intellectual assets. They switched over from being 90%
IP
physical assets
as
physical assets to being 90% IP assets. So basically, what has happened is that everybody is patenting everything, and nowadays you have a problem creating a new power cable. This is getting much more complicated, and this is one of those things that are stopping the pace of technological advancement.
Okay, are you basically in favor of changing the patent law? That's what you're talking about.
Yes.
Okay.
Yes, because the 486 and the Pentium is when the actual IP wars started, real IP wars. Before that, Intel was okay. They were fighting the different other manufacturers on the based on the trying to explain why they stole their IP and so on and so on. But since they couldn't patent the 586 the number, they decided to go with Pentium. And this wasn't just a surface idea. This was an idea that ran much more deeper.
Yeah.
The problem was that they wanted to patent everything. They were trying to close the infrastructure down, and the next time when this thing was broken was when they had to implement the 64-bit architecture from AMD.
Yeah.
And this is one of those agreements that were surprising, because Intel did whatever they could to block everybody from using the same technology, and then suddenly they had to reuse the technology from it.
Actually, 64-bit and those parts of the agreements were a little bit after the main event that took place between Intel and AMD, which was Global Foundries.
Yes,
Yeah.
yes,
This
yes,
was
yes,
just a
yes,
little
yes.
bit later. After that, after all of the hoopla about this, they threatened to cancel AMD's license in 60 days, whatnot. I remember that vaguely from our journalistic days because that was so interesting. The result of that was a large, let's say, co-licensing agreement and whatnot, which probably still stands to this day. I don't know what's written there. It's difficult to see, but I see that they still coexist on the market. So that's that, because all of the others are gone.
But it's not that just the agreement about coexisting, it's also the agreement on the ISA.
Yeah.
The thing is that AMD won that war, and I think that one of the reasons why we have any competition right now is because I have a sneaky suspicion that AMD is getting a lot of money out of it, and it is one of those things that is keeping it afloat. Because they can always basically they own most of the 64-bit instructions or architecture right now, and they have think that they have a healthy reserve when it comes to dealing with everybody else on the market, because they are able to experiment then.
Okay.
And it's just one of those things. Call me simple, call me too simplistic when it comes to understanding technology, but I would say that there are some things in the licensing agreements and different things that have happened that makes them, some of them, much more interesting from the perspective of the entire market.
Okay. Sounds good.
Okay. Anyways, thank you for joining me talking about Intel.
Yeah, we're gonna keep on joining each other talking about Intel in the more than a few next episodes. Next time we're gonna go through the Pentium generations, so Pentium, Pentium MMX Pro, Pentium 2, 3, 4, Pentium D, Pentium M. I think we should basically stop at the core architectures, or roughly in that area. Because there will be a lot of topics to cover when talking about Pentium, Pentium MMX, and Pro. And then little by little, it's going to get a little bit less interesting in terms of the innovations through Pentium 2, 3, and 4. And especially Pentium D, which is, if you ask me, one of the worst processors ever made, only rivaled by some of the other Intel processors from that era. But more about that next time around. So
I'm just going to say that from all the models that you mentioned, it is obvious that the plethora of models that came when 486 came to the market is nothing compared to the chaos that Pentium has created.
yeah, but there were some excellent CPUs on the way, actually, from all of the generations. Pentiums, the MMXs, the Pros, the 2s, the 3s, the 4s, all of them had models that were really excellent. That being said, a lot of them were indescribably expensive as well, but more about that next time around. Okay.
Okay, see you.
See you next time. Bye.
And thank you for being with us.
Yeah. Bye-bye.
Bye.